artificial intelligence-driven supply chain planning algorithms. AI-driven supply chain planning leverages complex algorithms to enhance efficiency, accuracy, and responsiveness across various supply chain functions. Organizations need to not only follow systematic steps to achieve performance outcomes, but also be cognizant of factors that present challenges in reaping associated benefits. The foundation of AI-driven supply chain planning lies in data collection and integration, i.e., gathering vast amounts of data from diverse sources. Internal data sources include sales history, inventory levels, production rates, order fulfillment data, etc. On the other hand, external data sources include market trends, supplier performance, economic indicators, weather conditions, social media sentiments, etc. Data is integrated into a centralized system, often facilitated by cloud computing, to create a comprehensive dataset for analysis. The next step involves data preprocessing to ensure quality and consistency before feeding the data into AI algorithms. In this stage, the data is cleaned by removing duplicates, correcting errors, and handling missing values. Normalizing helps in scaling the data to a consistent range to improve algorithm performance. Categorical data is often transformed into numerical values using techniques such as one-hot encoding. Feature engineering involves selecting and transforming relevant data features to enhance the predictive power of the model. Key variables that have significant impact on supply chain performance, for example, lead times, demand patterns, are identified, and new features are derived from existing data, such as calculating average lead times or seasonal demand variations. After these initial steps are undertaken, model selection ensues depending on the specific supply chain task. For instance, demand forecasting calls for time series models, for example, ARIMA, profit, regression models, for example, linear regression, gradient boosting, and deep learning models such as LSTM networks. Reinforcement learning models are used for inventory optimization, where these models learn optimal stocking policies through simulations. Optimization algorithms, such as genetic algorithms, ant colony optimization, and neural networks are used for route optimization so that efficient delivery routes can be identified. Once the models are selected, using historical data, the training phase enables the algorithm to learn patterns and relationships within the data using historical data, adjusting its parameters to minimize prediction errors. And the validation phase helps in evaluating the model's performance on a separate validation dataset to ensure it generalizes well to new data. Once trained, the AI models help with prediction and optimization of supply chain operations. These could include such areas as demand forecasting, recommending optimal inventory levels to balance holding costs and service levels, allocating resources and scheduling production runs to meet predicted demand efficiently, optimizing delivery routes, shipment schedules, and transportation modes to minimize costs and delivery times. AI algorithms then enable real-time decision-making by continuously analyzing incoming data and updating predictions and recommendations. With adaptive learning, the models adapt to new data, improving their accuracy over time. Automated adjustments help the system to automatically adjust supply chain parameters, for example, reorder points, production schedules, based on real-time insights. The final step in AI-driven supply chain planning involves a feedback loop for continuous improvement. Through performance monitoring, KPIs, for example, order fulfillment rates and inventory turnover, are tracked to measure the effectiveness of AI-driven decisions. Periodically, model retraining with new data helps in maintaining and enhancing performance. Running what-if scenario analysis prepares a firm for potential disruptions and optimizes contingency plans. Notwithstanding the step-by-step approach for using AI algorithms for supply chain planning and their associated advantages, many firms fail to reap those benefits. These challenges often stem from several key factors. Many companies struggle with the quality and integration of data from disparate sources within their supply chain. Inconsistent or incomplete data can lead to inaccurate predictions and suboptimal decision-making. For instance, if historical data is incomplete or inconsistent, AI algorithms may produce unreliable forecasts. impacting inventory management and demand planning. As an example, a multinational consumer electronics company implemented AI-driven demand forecasting software to optimize inventory management. The software struggled with integrating data from various retail partners, resulting in inconsistent demand forecasts. Due to this shortcoming, the company experienced issues with inventory levels, leading to excess stock in some regions and stockouts in others, impacting profitability and customer satisfaction. Companies face difficulties in implementing and fine-tuning complex AI models. These algorithms require specialized expertise in machine learning and data science to develop and maintain. Without sufficient internal expertise or resources, companies may struggle to effectively deploy AI-driven solutions and optimize them for their specific supply chain needs. Resistance to change within organizations can hinder the successful adoption of AI-driven supply chain planning. Employees may be reluctant to trust AI recommendations over traditional methods, or may lack the necessary training to interpret and act upon AI-generated insights. Without buy-in from key stakeholders and adequate change management strategies, companies may fail to leverage AI's full potential. For example, a global pharmaceutical company adopted AI-powered supply chain optimization tools to streamline logistics and reduce costs. However, middle management and operational teams were resistant to AI recommendations, preferring traditional planning methods. Despite the potential for cost savings and efficiency improvements, the company failed to fully realize the benefits of AI, resulting in missed opportunities for operational optimization. The upfront costs associated with implementing AI-driven supply chain solutions can be substantial. Companies may struggle to justify these investments without clear, measurable returns on investment, ROI. Moreover, accurately estimating the ROI of AI initiatives can be challenging due to factors such as implementation costs, ongoing maintenance, and the complexity of measuring intangible benefits, like improved decision-making. Integrating AI-driven algorithms with existing legacy systems and processes can be complex and time-consuming. Legacy systems may lack the flexibility or compatibility required to seamlessly integrate with AI solutions, leading to operational disruptions and delays in realizing benefits. For example, a leading automotive manufacturer invested in AI algorithms to optimize production scheduling and supplier management. Integration issues arose when attempting to link AI systems with existing ERP platforms and legacy systems. Delays in data synchronization and decision-making processes affected production timelines and supply chain visibility, impacting overall operational efficiency. In industries with stringent regulatory requirements or ethical considerations, implementing AI-driven supply chain algorithms may raise concerns about data privacy, algorithm transparency, and compliance with regulations. Companies must navigate these challenges to ensure that AI solutions comply with legal and ethical standards while delivering operational benefits. For example, a global food and beverage conglomerate implemented AI algorithms to optimize its supply chain, including procurement, production planning, and distribution. The AI algorithms used by the company to optimize procurement decisions inadvertently favored suppliers with lower costs, sometimes sourced from regions with questionable labor practices or environmental standards. This raised ethical concerns within the company and among stakeholders, including customers and advocacy groups. Additionally, there were regulatory concerns related to compliance with labor laws, environmental regulations, and fair trade practices in different regions. The ethical and regulatory concerns posed reputation risk since negative publicity and stakeholder backlash affected the company's brand reputation and consumer trust. The company faced compliance issues since regulatory authorities scrutinized the AI algorithms and supply chain practices, leading to potential fines or legal repercussions for non-compliance. The company had to reassess its AI algorithms and supply chain policies to ensure alignment with ethical standards and regulatory requirements. This involved revising procurement criteria, enhancing supplier vetting processes, and implementing transparency measures in supply chain operations. Overall, addressing these challenges requires a holistic approach that includes improving data quality, investing in AI expertise, fostering a culture of innovation and adaptability, managing costs effectively, ensuring regulatory compliance, and aligning AI initiatives with strategic business objectives. Companies that successfully navigate these challenges can harness the full potential of AI-driven supply chain planning to achieve competitive advantages in today's rapidly evolving market landscape.